and welcome to Algebra Workout. In this episode we'll be looking at trigonometry. I'm Sally Ann Keyser and once again I'm joined by Alan Borthwick.
What we'll be doing is looking at some basic techniques in trigonometry and going through some trigonometric identities. We'll be going through some examples, each of which Sally Ann is going to work on, and I'll be adding my own contribution to each of them.
Okay, let's get started. Look at this first example. I've got that tan theta is equal to 2, and I'm asked what the sine of theta is and the cosine of theta. Well, the way I'd make a start on this is to use a right-angled triangle. If the tan of theta is equal to 2, then that means that in this right-angled triangle I would let the opposite side have a length of 2 units and the adjacent side have a length of 1 unit. The tan of this angle in a right-angled triangle is the length of the opposite side divided by the length of the adjacent side, and the sine is the opposite side length divided by the hypotenuse length. So I need to know the length of this other side. Well, by Pythagoras' theorem, it's the square root of 2 squared plus 1 squared, which is root 5. So the sine of theta is 2 over root 5. That's opposite over hypotenuse. And I know that the cosine of theta is the adjacent side length over the hypotenuse side length, which is 1 over root 5. So I've solved the problem. But it's more complicated than that. By using a right-angled triangle, I've assumed that theta is less than 90 degrees. And as it happens, there's more than one angle theta, for which tan theta is 2.
Okay, first it'll be useful to go through some basics of trigonometry. I'll show you how sine and cosine for general angles arise from the unit circle. Okay, if I take two axes and a circle with radius 1 centred at the origin, I can consider a point on that circle which is free to rotate all the way around it through 360 degrees. Now let's watch it go round again, this time showing the angle it sweeps out. This time, let's stop where there's a right angle triangle where the ratio of the y length here and the x length here is 2 to 1, as Sally Ann had. The tangent of this angle is then 2. Now remember that the sine of an angle is the opposite over the hypotenuse. Y over 1, the hypotenuse being 1. In the unit circle. So sine theta is y. Similarly, cos theta will be x. And tan theta, which is sine theta divided by cos theta, comes to y over x. Now let's move on. Let's move this point further round until we get another triangle with the ratio 2 to 1. The ratio 2 to 1, the y length to the x length. So is this angle also an angle with tangent equal to 2? The answer is no, because the tangent is y divided by x, and in this case x is negative. So we have a positive y and a negative x, so the tangent of this angle is negative 2. Let's move on. Moving round to the next part of the circle, if we stop again, y length to x length ratio 2, and in this case y is negative and x is negative. And dividing a negative by a negative is a positive. So here we do have the tangent of this angle equal to positive 2. And let's move on to our last quadrant here. Okay, at that stage, y length to x length is 2. So it looks like the tangent will be 2, but unfortunately, the x is positive and the y is negative. So the tangent of this angle is negative 2. So in fact we have two places throughout the circle where the tangent is equal to positive 2, and that's in the top right and in the bottom left.
Thanks, Alan. So you can see now that there's more to the original question than my own right-angled triangle. Constructing a triangle and using Pythagoras' theorem to find sines and cosines is fair enough for acute angles, but there's always more than one angle that has a particular tangent, or indeed sine or cosine. If I think of the circle as divided into 4 quadrants, 1, 2, 3 and 4, then as Alan showed us, the tangent of an angle is positive in this first quadrant and also in this third one. Well, what about the sine and cosine? Sine is the y-coordinate of the point 1, 0 as it rotates, so it's positive in the first and second quadrants only. And since cosine is the x-coordinate, you might just want to work this out for yourself. Cosine is positive in the first and fourth quadrants. Everything is positive in the first quadrant, of course, because both x and y are positive here. OK, I want to get on and do a second question. If the tan of theta is 2, what are the sine of 2 theta and the cosine of 2 theta? Now, I can't do this by just drawing a right-angled triangle and looking at it. There are some equations known as trig identities which allow you to interpret thetas and 2 thetas in this kind of situation. Before I make use of them, I'll hand over to Alan for a refresher course in trig identities.
Thanks, Sally-Ann. OK, the identities you'll need here are expressions for sine 2 theta and cos 2 theta. They're called the double angle formulas. Sine 2 theta equals 2 sine theta cos theta, and cos 2 theta is cos squared theta minus sine squared theta.
And they're in terms of just theta, so they'll be useful to me in my example because I know sine theta and cosine theta.
Exactly. And as it happens, there are more ways than one of expressing the cos 2 theta identity. You'll know that cos squared theta plus sine squared theta equals 1. Now that's just another way of writing Pythagoras' theorem. X squared plus y squared equals 1. And using this, we can write sine squared theta equals 1 minus cos squared theta. Place it into this expression here, and we get 2 cos squared theta minus 1. Don't worry if you don't follow it exactly, that's what happens. So by a similar arrangement, we can replace the cos squared and get 1 minus 2 sine squared theta. And therefore, you have 3 expressions to choose from for cos 2 theta. These 3 expressions.
OK, I'll use those to get my answer. I know that the tan of theta is equal to 2, and from my right-angled triangle, I know that the sine of theta is equal to 2 over root 5, and the cosine of theta is equal to 1 over root 5. So first of all, what's the sine of 2 theta? Well, there's only one expression to choose from to work this out, and it's the top one. The sine of 2 theta is equal to 2 sine theta cosine theta. And substituting my values in, that gives me 2. Sine of theta is 2 over root 5, and the cosine of theta is 1 over root 5. And multiplying that out, that gives me 2 times 2 is 4 over root 5 times root 5 is 4 over 5. So I've done that one. And what about the cosine of 2 theta? Well, I know cosine and sine, so I could use any of the 3. But suppose I use the last expression for cosine 2 theta. So that gives me cosine of 2 theta is equal to 1 minus 2 sine squared theta. So substituting in my values, that gives me 1 minus 2 sine squared theta is 2 over root 5 all squared, which equals 1 minus 2. 2 squared is 4, root 5 squared is 5. 1 minus 2 times 4 fifths, which equals 1 minus 8 over 5, which equals minus 3 over 5. So the cosine of 2 theta is equal to minus 3 over 5. You might want to have a go at solving for cosine 2 theta by using the other 2 identities. So I finally solved both problems, the first one geometrically and the second by using trig identities.
Excellent. Well, I hope you've learned something from our tour de force of trigonometry. But you need to remember to be careful with trigonometry because there's always more than one angle whose sine, cosine or tangent you know. The trig identities are also really useful for doing algebraic manipulations of trigonometric functions. So try to remember them, they're always very handy. Okay, good luck with your own exercises.